Just while we're getting set up, I just want to introduce you to my friend here. I'm very excited to come and give you this talk. So excited that I actually need an assistant. Here he is here, this is Skippy. When we get my slides up, you'll actually see that I'm from the SETI Institute. At the SETI Institute, I run the colloquium series there. Has anyone heard of the SETI Institute colloquium series? A couple of hands around? Yeah, there's some people. So we put all our talks up on YouTube. So we now have 434 talks up. We've been running for about 8 years. Most of the talks, well, all of the talks have something to do with the Drake equation, which is SETI's guiding principle. And we have probably 30% of the talks are on Mars topics. We actually have a lot on exoplanets. So if you're a secret, I know everyone here is all about Mars. I am too. But I also admire the exoplanet field greatly. And they just had the biggest discovery of my life, I'm sure. I mean, at least I can't predict the future, but it was pretty big last well, it was a couple of weeks ago with Proxima. We had the first author give a talk, and that's available on our YouTube channel there. It's actually, he was remote. He's from the European Space Agency, and we wanted to be timely and get him at the time when this life-changing, universe-changing event happened. So if you're interested in getting signed up for the seminar series mailing list, that's what Skippy's doing there. He's looking after the sheet there that you can sign up on. So feel free to do that. And let's skip into this talk. All right. That's one of the Martian talks is from Aaron Zent. Aaron's specialty is subsurface water ice. And I'm going to say straight up front, I'm going to declare my bias. I'm not talking about water ice today in the subsurface. We've had fantastic talks from Jen and Guillermo. I'm going to be talking about surface water ice today. You can also follow us on Twitter. Maybe you can't see the website down below, but it's seti.org/talks. All right, so today I'm going to talk to you in basically 3 chapters. The first chapter is going to be about what we know about water on water on Mars. And we've heard it mentioned by Guillermo that the north is the place where all of the water is. So I'll just talk briefly about that. Then I'm going to have the smallest chapter, chapter 2, is a little bit about water ice down in the south polar region as well. There's a small amount of it, and I'll talk to you about how strange that is. And then I'm going to just summarize a recent study that we did looking at the amount of water ice that's deposited on top of the North Polar Cap during a summertime. So we're talking about current day conditions and climate. As Guillermo again mentioned, the thinking is that the Mars polar caps were formed in about 3 to 5 million years. So we're talking about recent stuff, not the Noachian on Mars, which is also very cool, but that's not what I'm going to be talking about today. Doesn't mean you can't ask me questions about that too later on. All right, so let's go into our first chapter. All right, so more water in the Martian northern hemisphere. Firstly, I'm just going to talk to you a little bit about the primary driver for why there's water ice, more water ice in the North Pole, and that's eccentricity. Mars is has a very eccentric orbit, far more eccentric than Earth. And so, for example, you can see here we have basically, we have the eccentricity of Mars here is very high compared to the Earth, so that a northern summer lasts only 179 sols. That's one Martian day, which is about the same time as an Earth day, but slightly different. And yet the summer the winter is only 153 days long. So the winter is short, or it's a short, intense summer in the south, or it's a long, moderate northern summer. Okay, so let's go through some more diagrams to sink that in. I'm going to be talking a little bit about solar longitude, so I wanted to introduce that concept to you. So basically, solar longitude is a measure of the season, the time of the year, running from 0 to 360, so it's a lot like just degrees. It's basically the position of the sun relative to Mars, if you're looking on the Martian surface, in the surrounding star field. So that's why we call it solar longitude. So basically, you've got from L sub s 0 to L sub s 90 is Martian northern spring. We'll talk a little bit about that. And then 90 to 180 is a really cool period of Martian North Polar summer. That's what I'm going to be talking most about in the final chapter. And then we have spring in the south and what we call summer in the south as well. 270 to 360 or we loop around to 0 again. All right, so that's what L sub s is. All right, now these videos just show you the residual cap. So I'm going to have to explain what I mean by residual cap in both of the hemispheres. On the left, we have the North Polar Hemisphere. And this is a water ice-rich ice cap. This is the residual cap that remains when all the springtime has finished and all the CO2 is the CO2 that gets deposited on top of the surface during winter because it gets so cold has all disappeared. This is what remains after that. So this is often what you see during presentations like this. But I just want to explain that that's the residual cap. It's also sometimes called the North Polar layer deposits because we're looking at this massive piece of ice, you actually see these massive layers in it, which is like, for a geologist, that's like, whoa, heaven, you know. So lots of people fantasize about what we'll be able to discover in those. It's only 3 to 5 million years, but it's still a large amount of Martian time, and it's very important for us, for the people who might be the settlers on Mars. All right, so in the south, it's not so friendly. Basically, this residual cap here is smaller, and actually it's not even water ice. The ice that you're actually seeing there in the residual cap, it's actually cold enough and the conditions are right that CO2 never disappears from it, even during the summer. I'll show you a little bit more about what we've discovered. It does happen during the summer, that a little bit of water ice gets deposited on top. But at the end of springtime, it's all CO2 ice. So this is what the residual caps are. And we knew this after the Viking measurements. In fact, these are maps produced by the Viking images. All right, so stepping on. So after Viking, we then had Mars Global Surveyor. On board Mars Global Surveyor, this was started in 1997, these observations. There was an instrument called a thermal emission spectrometer. That was used to try and map water vapor around Martian surface. That was done for several years. Since you're now experts in L sub s or solar longitude, I can show you a graph like this. And don't get too scared when you see this L sub s. So basically, this is the period of northern summer, and red are intense periods of water vapor in the Martian atmosphere. So we're looking at water vapor in the Martian atmosphere as observed from orbit and averaged over these local spots. You can see they're actually made up of pixels here. And these are for different Martian years, so you can see the repeatability of this cycle. So always we get higher amounts of water vapor coming off in the Martian North Pole, in the Martian northern summer, I should say. And at the top, Tess took the measurements on the second, third, and fourth lines. The top line is actually taken by an instrument called XRISM, which I'll be talking more about in just a sec. And XRISM also saw the same intense high. There's a lot to be said about these graphs. They're fantastic, but I'll just emphasize that, I'll just use them to emphasize today the amount of water ice, water vapor is much stronger in the north. All right, this is the obligatory terrestrial comparison, which tells us lots of things. So this is a MODIS image taken by the MODIS Terra spacecraft around Earth. This is taken 30th of January 2005. This is a global average of, sorry, not a global average. It's an average over these global mean water vapor in centimeters. The previous maps I showed you were actually in precipitable microns. All right, so this really gives you a straight up that there is a huge difference between the two planets in terms of their current amount of water vapor. It's not a fair comparison, okay? There's a much thicker atmosphere, there's going to be more water available on Earth. And I'm not really saying one is better than the other. They're just different planets with different water cycles. But it is interesting nonetheless. You can see things such as the Earth has very little water vapor in the poles. There are places on the Earth which, due to topographic reasons, are very dry. For example, the Atacama Desert, just here in Chile. Australia, you'd think, Skippy tells me anyway, that it's very dry. I thought it was very dry. I thought it was very cold until I came to Maryland. But no, it's actually comparatively wet compared to the Atacama, for example. Or even Antarctica. Antarctica is a great Martian element. All right, so why is this? Why is it so? Why do we have more more water in the North Pole at the moment? Well, I mentioned one cause, and that's eccentricity, which has been favored for a long time. But also in 2002, Mark Richardson and John Wilson put this paper into Nature, where they were talking about just the topography of Mars as a driver for the water being trapped in the North Polar region. So essentially, the North Polar region is much lower than the South Pole. So you can think of it more or less as a potential well that the water has to escape from, so that once it gets into the north, it's less likely to get into the southern polar region. And this is something that isn't going to change unless the global tilt of Mars changes, which has happened in the past, of course. But in Martian, current day Martian climate, this is going to be an important constrictor of water to the North Polar region. All right, I love this image. This is actually an image that was put together by the Phoenix lander. That was landed at 68 degrees. We'll probably hear a lot more about that from Mike Hecht after me. So what they did here was they were looking at water ice in the atmosphere, firing a LiDAR just up above the Phoenix lander and just watching these clouds go by. So basically, they almost saw the water ice clouds getting down to the surface. These are all taken during the polar night, but basically this is really great evidence that it actually does snow during even during summer. This was obviously during summer because Phoenix was solar powered, so it couldn't run during the winter. All right, and this is just a fantastic video put together by Wendy Calvin and the Marcy team, showing you a little bit of the development through spring. This is what you're seeing here, this fuzzy outline, is actually the CO2 cap retreating during spring. It's disappearing, and we can see it as a sort of transparent layer on top of the surface. And then once it's finally disappeared, you'll see the residual cap pop out. So that's what we're seeing happen, is this CO2 ice coming off during the springtime as things are warming up, and then finally, bam, we get a residual cap. You'll see it actually brightens a lot too when we get the residual cap at the end. Now, just to familiarize yourself with some things that I'm going to be talking about, this here is Mrs. Chippy's ring, or the North Polar outlier deposits. These stay every year, so they're very stable at the moment, as we understand it. This is Gemini Lingula down here. This looks like a little bit of a tongue, and this is Casbah Boreal, is this massive canyon there that's carved by winds. And you can almost make out the layered structure by looking down on top of the cap. But the best way is to look at high-rise images if you've ever been to the high-rise website. All right, so, and then after a while, what happens at the end of summer is you get this buildup of clouds traveling around the polar vortex, essentially. And you'll see that actually baroclinic activity is driving these wispy vortex-like clouds as they go across, and then the cap becomes obscured again by what we call the North Polar hood. So this is the basic development that happens every spring and summer in the North Pole. All right, so I mentioned my bias at the start. I'm just going to talk about surface water ice. I'm not going to talk about the rich inventory of subsurface water ice, which we've used radar to get at. But today I'm going to be talking about another instrument that was on Mars Reconnaissance Orbiter, which has been returning data since 2006. And XRISM is ideal for looking and distinguishing between the CO2 and water ice on the surface. As you saw with that Martian image, we didn't really have a clue what ice we were actually looking at. But by looking at it with a spectrometer and looking at it at different wavelengths, what we can do is separate out the water ice from the CO2 ice because they look very different at different wavelengths. Okay, so it's a little bit like if you had a camera and you took a picture at a black and white camera, and you took a picture at one wavelength, let's say 0.6 microns, which is in the visible, that's what we can actually see. And then you took another camera picture at 2 microns, which is where water ice has a big absorption band. Well, water ice there would look very dark, but CO2 ice would still look quite bright. Okay, so we can use that, and we actually get a whole string of pictures. We actually get, from XRISM, we get over 400 bands, images taken at different wavelengths that we can then use. And we can turn them into spectra, and you'll be seeing some of those wiggly lines coming in some of the slides, and I'll try to be as helpful as possible and interpret them for you. All right, this is just what I mentioned. Basically, you can envisage this. It's called hyperspectral imaging. You can envisage it as a stack of images, and we're just drilling down to take a spectrum. And then the spectra turn out a little bit like this feature that I see that I've put on the right-hand side here. This is actually water in a clay mineral, so this isn't water ice, but I'll show you some spectra of water ice and CO2 ice. All right. So this just shows you where on MRO XRISM actually is. I'm sure everybody is aware of the HiRISE instrument. That's the whopping Great Spice satellite in the middle of the observation deck here. That's HiRISE. XRISM sits alongside it. This is the CTX. So it's HiRISE here on the left, CTX in the middle. Sorry, not CTX. That's the Mars Climate Observer there. Mars Climate Sounder, I should say. And this is XRISM here. XRISM can gimbal a little bit, so it actually looks through the atmosphere at different angles in order to try and get rid of the interference of the atmosphere. Or if you're an atmospheric person, is try to get rid of the interference of the surface. All right, so what I'm going to be telling you about now, this slide is just showing you that this is a string of papers that have come out in different publications. We started with 2010 looking at the South Pole, the South Polar Spring Retreat. So we're looking at CO2 ice coming off the South Pole. And then in 2012, we looked at the same observations in the North Pole. 2014, we looked at summer observations in the South and found small amounts of water ice deposited. And then just in 2016, that's the study that I'll tell you most about at the end in the final chapter. All right, so let's take a look at the tiny amounts of water ice. I've mentioned that this paper was published in Bob's favorite Journal of Geophysical Research. So I've chosen to highlight this is a time in the middle of spring. You can see the Martian images here. This is the South Polar Cap. You can just make out the residual pole cap in the middle of the CO2, retreating CO2. What we see in the middle and on the right-hand side are actually XRISM maps constructed over a 2-week period and then put together as mosaics. So they're thin strips of XRISM observations. XRISM observations are about 10 kilometers wide. That's why they look like these spaghettified type of maps. But they give us a really great feeling for where the cap is pulling in. And we can automatically determine what's CO2 ice and what's water ice. So what I've got on the left-hand side is an interpretation map showing where the red is CO2 ice. This is on the right-hand side. This is this image here. That's all CO2 ice there, but just this little bit of blue down there, which indicates water ice. And if you look in the Martian images, you actually see that this looks pretty sort of ragged. This area here is called the cryptic region. It was found in 2000. And it's an area that turns dark as the cap recedes. And what we see with CRISM is that that part of the cap is actually showing water ice features rather than CO2. We still don't know why, but it's a very big mystery. You can ask me lots of questions about it later. All right, so moving on. We've also looked at, as I mentioned, in the southern summer for any signs of water ice. As I mentioned, CRISM is very sensitive to water ice, and so we can map very small amounts. This is a map of the residual cap. This is LCMS 304 to 311, basically showing you that it's almost entirely red CO2 ice with some small amounts of blue water ice up in the top left-hand corner in this representation. And then during the late summer, however, a small amount of water ice has mixed in with the CO2 ice. So there's something that's getting water ice onto the cap. Now, we're not sure exactly what that process is, but it could be that the CO2 cap is somehow disappearing and perhaps the water ice is being exposed somewhat. I'm more of a fan of the Aeolian explanation, which is the wind-blown explanation, that we might get wind blowing water ice from the corners or the sides of the cap onto the South Polar Cap throughout summer, which is an interesting sort of process. All right, so let's move on to the final chapter. Now this, it starts with this North Polar Spring, of course. We had a JGR paper on the North Polar Spring retreat. Here I'm showing you what CRISM sees for the North Pole retreat. This is just one example of a very interesting process. Again, red is pure CO2 ice. You'll notice you don't see any. We do not see pure CO2 ice as CRISM. CRISM has it all. In this mapping mode, we have 180 meters per pixel resolution. But note the contrast with the South Pole. We do see some CO2 ice signatures, but it's all mixed in with water ice. Here you see the blue is actually water ice, and the cyan colors is where the CO2 ice remains. So even when you look at it in a Martian image, you actually think, oh, well, all this is, it looks like CO2 ice. It's all CO2. But actually, it's not. All around the edge, it's water ice. And it's only in the middle that we see this CO2 ice. Now, previously, the test instrument had been shown to been used to show this, but they couldn't actually sense the absorption bands that CRISM could do. So we actually found in this part that we're actually getting asymmetric retreat of the CO2 caps. There's more water ice being deposited here. So where was this coming from? Well, one option is that it might be this, what we call a Huben process, where water ice getting on top of the CO2 cap. But thinking about that, it didn't really work because that's a more symmetric process. So we had to come up with something that was asymmetric. And this is what we came up with, was that the North Polar outliers are actually getting exposed. A little bit of water ice is coming off them using wind, wind explanation, or possibly some sort of sublimation as well. And that is then getting blown onto the cap, and that's what we're seeing with CRISM. All right, this is the 2016 paper that's all about Martian polar sublimation and deposition. This is a figure of water ice taken from the Omega instrument, which is run by the ESA, the European Space Agency. And they looked at this region called Point B. It's an area in Gemini Lingua. And they looked at it throughout the early summer period. What they saw was from LCMS 90, which is the start of summer, through to midsummer, which is LCMS 127, they actually saw these bands growing. So you'll actually see the dark line is here, and then these bands grow, they grow deeper. And what they thought that was happening was large grains were being formed on the cap, and that was probably happening through a process of sublimation during the early summer. However, they didn't actually publish any data after that. So I was a little bit confused as to why, and I think that it's probably because they couldn't quite interpret it. When we have a more complete data set with CRISM, we're able to do a better job of interpreting what we see. I mentioned Point B. Point B is this area here in Gemini Lingua. just here. So we're just looking at spectra of that particular area. But what we were able to do with CRISM was we were able to map the band depth, and this is a proxy for the band depth, and how that changed just during late summer. So actually say the band depth is very low during the midsummer period, which is where they left off. But then it actually shrinks. So it's shrinking, the band depths are shrinking throughout late summer. So what could be happening there? Well, what we actually think is that there's some form of water ice deposition of fine-grained particles that's actually making the band depths shrink. Okay. So what we can do is we can map where that occurs across the whole cap. All right. So CRISM gives us the ability to see that process across the whole cap. But we'll investigate at point B just to check that we're not fooling ourselves as to what's happening. And I will motivate this, this particular study more in the last slides. But here we have the money shot, if you will. So this is, on the left, is the CRISM observations of point B during the same time that Omega was actually able to. We saw the bands grow, but then they pause at about 122, Alcibus 122, and they stay stable till about Alcibus 135 at this point B. Yeah, and then we actually see the bands shrink, as I mentioned, and probably due to fine-grained ice getting deposited. All right, we'll skip this. So we were able to then use a radiative transfer model to work out how much water ice is actually being deposited. And we were able to work out how much gets deposited by subtracting one map from the next and work out how much gets deposited over the entire North Polar Cap. So here is the map that shows you in the late summer where water ice is getting deposited and where it is getting sublimed. And you'll see that there are areas in dark blue around the edge of the cap that are where water ice is getting sublimed, and it's stable in the center of the cap. What this allows us to do is work out when these areas are in net sublimation and net deposition modes, what we can do is then use that to interpret our current history of the Mars polar cap. Because we found that there was areas around the periphery of the cap that were turning blue, i.e. subliming, that gives us a clue that perhaps the reason why the North Polar Cap is as big as it is today is because of the stability of the water ice, as we're seeing with CRISM. All right, so then we could use this data that we now know how much is deposited every year. We can use this to interpret the history of climate of Martian climate throughout the last 3 million years. Once we get to Mars, we can also use that to drill cores and find things such as organics and methane, so we can work out the climate history of methane. But we need observations like this to tell us what's the time interval between the top and 1 meter down in the North Polar Cap. And of course, we want to be able to, when we get Martian settlers there, we want to be able to sustainably use this water resource. So we want to make sure that we're not taking too much from the North Polar Cap and drying things out prematurely or making things worse for other Martian settlers. So I'll leave it at that. Thanks very much for your patience. And I'll take any questions. One question.
So I was wondering, how much water are we talking about for future Mars settlement? And how easy would it be for them to actually extract it since there's so much CO2 ice as well?
Yeah, that's a great question. And this will be something that there'll be much debate about in coming Mars Society conferences, I'm sure. What we mapped was 140 precipitable microns were deposited on top of the cap per day, in fact, in the North Polar Cap. So that means you could just send a bucket up there or some sort of robotic instrument that would then collect that, that water ice. But then you've got to ask yourself, well, am I then going to be able, well, I'm not refreshing the cap, so that is, I'm getting a net sublimation from the cap, I'm actually taking that resource away from the North Polar Cap. It's going to shrink, and it's going to be less stable. So these sort of measurements give us a first-order bird's-eye view on how to do our due diligence in using water ice as a sustainable resource for Martian settlers.